we are now recording. Get the slideshow set up from the current slide. And I can't do any of this until I get Screencast-O-Matic up because it doesn't allow me to do that. Let's do hide presenter view and turn on the projector. Cameron, okay. What's that? Yes. Okay. We were in the middle of page 648. All right. Tony's here.
I was painting a very vivid picture with my mind.
What's that?
I was painting a very vivid picture with my mind.
I see. Okay. There you are. Okay. Just having trouble. It came on right as I was trying to mark you present. Okay. Good deal. We're right in the middle of page 646. This is section 12.3. And I think I told you last time, this is not a section I usually run out of time in 202 before we get to this, but it is a pretty important section, so I thought since we were going back and picking up stuff, let's pick this up as well. A couple of ways to define the dot product. The first was, of course, the sum of the products of the corresponding coordinates or components of vectors, or magnitude of one times magnitude of the other times the cosine of the angle in between, which then led to, in the middle of the page there, the first thing they don't show on the slide, but let me get my pen activated. Okay. Was this, that the cosine of theta, this is just a rework of the second definition we had, is equal to dot product, say of two vectors v dot w, divided by the magnitude of v times the magnitude of w. Because before we said the dot product was magnitude of one times magnitude of the other times the cosine of the angle in between. Or the cosine of the angle in between is, divided by magnitudes. Or take this one more step, take the inverse cosine of both sides, and this is what you've got. Now, if you remember inverse cosine, it's only defined where?
Between like pi halves and negative pi halves?
No, you're thinking sine or tangent, inverse tangent or inverse sine. Cosine is 0 to pi. So this is always going to come out 0 to pi. Okay? Always. Now, if you're looking for another angle, you just add 180 to or pi to it, and you'll get that. Okay. Okay. We had, let's see. I can't remember. Were we actually doing the examples or was just doing a slideshow? Huh? I don't remember either. Yeah. The example 2 is find the angle theta between two vectors. How would you go about doing that? Oh, and this is interesting because we probably don't think of, let me go and do that then. All right, what I'm going to do is clear this off the screen. That's not what I wanted. Okay. Here's the two vectors. V is 362. W is, these are vectors, as angle bracket, vector notation, 424. Okay. Now, that would be pretty miserable to try to find the angle between those, because it's in 3 space. Okay? There's not any good thing like there is in two space. You can find the angle pretty easily, or you can find it. Three space, not, except through dot product. So find the angle theta between these two vectors. How would you do that? There it is, right there. Inverse cosine of, and what's v dot w? Twelve plus 12 plus 8 divided by, what's magnitude of v? Square root of 9 plus 36 plus 4. Yeah, this is 7. And this one is the square root of 16 plus 4 plus 16. 32 and 4, 36. That's 6. So what do we have here? Inverse sine, cosine of 24 plus 8 is 32 over 42, and then plug that in your calculator, right? That's the same as,
What page are we on?
this is page 646, section 12.3. So if any of you got a calculator, plug that in, see what inverse cosine of 32 40-seconds are.
I do not today.
Okay. And by the way, that could be reduced to 16/21 if you want to plug in smaller numbers.
Same number of digits.
Yeah. Second?
It says the same number of digits if you're
Right.
plugging it in.
If you're using a calculator anyway, what difference does it make?
What do you get 42 from?
Magnitude of v would be the square root of the first component squared plus the second component squared plus the third component squared. That's 9 plus 36 plus 4. That is 40, 49, that's 7. Got it? Yeah. Okay, good deal. What's that? Is that a degree? Yeah, in degrees. Okay, in radians that would be about, because, just face it folks, most of the time in calculus, they'll be dealing in radians. Real life you deal, huh? Second, 0.707, is that what you said? 705? 7, okay, yeah, good, close enough. All right, now, let's think about something else. What if V and W are both non-zero vectors? Both of them. Neither one of them can be the zero vector. Why not? They're the zero vectors. What's their magnitude? 0, you can't divide by 0. So we do not allow that. Not the zero vector. But what if you came up with the dot product being 0, but neither one of them were zero vector? What would that tell you? It's the inverse cosine of 0. This is a 0 up here, not a 0 down there.
I want to say it's 1, but like pi halves.
Pi halves, exactly. It's pi halves. And pi halves, theta would then be pi halves, which means perpendicular. So anytime you have two vectors whose dot product is 0, that means they're orthogonal vectors. And that is a given, okay?
And that's what we're going into now.
Yeah, that's perpendicular orthogonal vectors, okay? And the little statement there, let's see if they give a slide. No, they don't. Well, they might, okay? These are the two that we just did. I didn't realize we had a slide of it. Those are the two we did. I said, not too easy to measure in 3 space. You tell us, number one, this is 2-dimensional. You're trying to do this. There's your angle in between that. And the cosine of that angle anyway was, well, the angle was 0.7 radians, which is, what did you say, 40-some degrees? When you first did it in degrees? 24. Okay. So,
40, he said 40.
huh?
40.4.
Oh, 40 point, okay. So, yeah, that, I was going to say this is, but even then, this looks like a bigger angle than what you just said. So it's really hard to do it graphically and come up with anything, but yeah. But 40 is less than 45. That looks like it's closer to 90, but it's not, obviously. Okay. So, that said, and here's what we just concluded. I'll do it here. Doesn't really matter. Okay. That any two vectors are orthogonal if and only if. That means this is an arrow that goes this way and going this way. If they're orthogonal, then that means the dot product is 0. If the dot product is 0, it means that it has to be orthogonal. So that's an if and only if deal there. And we will use that quite a bit. One special case of that are your let's see, they have special names for them. I can't think what it's called. I don't think they're going to say it either here. Your standard basis vectors, that's one way of expressing it. I, J, and K, the dot product between any two of those is 0. Standard basis vectors are mutually orthogonal. They have length of 1. So therefore, not just standard basis vectors, standard basis unit vectors are mutually orthogonal and have length of 1. Length of 1 means they're unit vectors. Okay. Oh, okay. This is the figure we're going to use for example 3, so let's just do it. Testing for orthogonality. Determine whether vector v here that you see listed there, vector v is 261. Vector u, oops, I just did something. I reserved the hat designation for a vector to be a unit vector. I'm used to naming unit vectors u, so I tend to put a hat on them every time, but I'll try not to. Okay, 2, -1, 1. Can you look at that and tell me whether it's a unit vector or not? It's not, okay. Okay, it looks like water, but it's not. Okay. All right, -4, 1, 2. You're sort of gross, you know that? Okay. All right. Now, the question is, determine whether V is orthogonal to U or W or both or neither. How would you do that? Do a dot product. What's the dot product of U and V? 4.
-6.
That would be a -2.
Okay, 1.
+1? No. Okay? How about U and W? I mean V and W.
-8.
-8.
6. 7. -2. +2 and 0.
Ding, 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 ding. Yes. V and W are perpendicular. And you see in 3 space drawn on a 2-dimensional board. Can you tell those are orthogonal? They don't at all look like it. Okay, if they drew them right, which I assume they
It
did.
kind of looks like if you
It looks like
if you look
that
at
has
the
a
y-axis,
Huh?
and if you look at the y-axis and the x-axis, they
Right.
kind of go right along with those, so it kind of makes sense.
Yeah,
They are-
okay. Looking at the back side of these, yeah. Just twist this up a little bit. It looks close anyway.
But also the U would look orthogonal to W, kind of.
Right, if you use this one, yeah. But so you can't trust that. And U and W are probably nowhere close.
No,
Let's
they're
just
not.
see. That's -8, -9. Yeah, that's -7. Okay, so yeah, you can't tell by looking in a 3-dimensional vectors plotted in 2 space. Just can't do it. Okay. Now, there's also a test for obtruseness, which is probably one of the few times in my life I've ever said that word in a sentence, obtruseness. Okay? Yeah. How are we going to tell that, whether there is an obtuse angle or not? Exactly. And what would that, how can you tell by looking at it? Not looking at the angle, but looking at the dot product. Okay. In the first quadrant, the dot product is always positive. Second quadrant is negative because cosine is negative in the second quadrant. So if it's negative, and when we just did that one, that one, the U dot W was negative because it came out negative. This one, V dot U, what was that, +1? I think is what it came out. Oh, it's -1, so that was obtuse also. Yeah, okay. Good deal. So I take it y'all want to do a couple. Vector V, 3, a new vector V is 3, 1, -2. Vector U, new vector U, 1/2, 1/2, 5. And a new vector W, 4, -3, 0. Okay? Determine whether these angles, well, let's just tell us what you can know about those 2 angles. V and U, U and V, whatever. That'd be 3/2 plus, that'd be 2. Yeah. Obtuse. Okay. How about V and W?
12 minus 3, which is 9, plus 0, which is 9.
Okay. Acute. How about U and V? U and W, sorry.
2 minus 3 halves, right?
Yeah. Be 1/2, right?
Yeah, 1/2.
Yeah. Yes. So that will be acute, but awfully close to perpendicular, because pretty small number. Make sense? Okay. Now, number 5. Find a vector orthogonal to W 1, 3, 2. Oh, that's just it. Find a vector orthogonal to W. Okay? What you want to name it? V. I thought Victor would say V. Okay. All right. There's tons of them. Pick one.
2, -2, 2.
Okay. 2, -2, 2. I think that's right. Is that in the book or you just make it up? Okay. Yeah, because that's 2 minus 6 would be a minus 4 plus 4. Absolutely. You could have done a 3, -1, 0.
But you couldn't have done 0, 0, 0.
No. We will choose not to have either one of these the 0 vector. I guess by definition it's perpendicular to every vector, but let's not go there. Yeah, very good. See what the book chose? They chose 1, 1, -2. I just couldn't find it there. There it is. That is such an orthogonal vector. Okay. Okay. Now they did go a little bit more formally. They came up with a parametric equation, and you choose anything that fits. Okay. Now let's look at a projection U that's parallel to vector V. Okay. Another important use of the dot product is finding the projection U parallel to V of a vector U along a non-zero vector V. By definition, U parallel to V is the vector parallel to V obtained by dropping the perpendicular from U to the line through V. Okay, let's see. Yeah, here's what we were doing a few minutes ago. I didn't realize I had. I just completely walked over the thing. The angle between V and W is obtuse if the dot product is less than 0. Negative, in other words. Okay. All right, here we go. All right. The projection of U parallel to some vector V of U along V has a length of magnitude of U times cosine of theta. Okay? So here's your vector U, and here's some other vector V. Notice nothing said about either one of their lengths or anything else. So when we're talking about the projection of U onto V, that means you drop a perpendicular to V, and the projection of U onto V is then that magnitude there. There's U parallel. All right. Now, here's one way of looking at it if you need a visual to help you out. Picture V as your base, your floor, and go perpendicular up from that, infinitely high here, and shine a really bright light, okay? And the shadow that U makes on V, perpendicular from here, that's what U parallel is, okay? Now, they throw in something else here. Anyone want to hazard a guess what this represents? E sub V. That's the unit vector in the direction of V. Now that has nothing to do with U at this point, except that you can express this U parallel as some multiple of that unit vector, okay? So okay, let's also look at this. Think of what this is telling us. Here is U, and this is U parallel projection of U onto V. Okay. Here's that angle cosine, the angle theta in between. the cosine of this angle here is this, let me say it this way. Cosine of this angle times the magnitude of u gives you the magnitude of u parallel. And that's exactly what this is saying here. That projection of u parallel to v, projection of u as length u, magnitude of u times the cosine of the angle in between. Hypotenuse, adjacent side. Okay. That leads to theorem 3. Talking about these projections, and this has relevance to what we were saying before, that illustration. All right. Projections, let's assume that v is not the zero vector. In fact, let's also assume that u is not the zero vector, okay? We don't like messing with the zero vectors, okay? I don't anyway. I have trouble even picturing it as a real vector, okay? But assume that v and u are not zero vectors. This is a vector, bold 0, that's the vector. The projection of u along v is the vector. This is a vector also, and it's the projection parallel to v is u dot ev, that was that unit vector in the direction of v. U dot ev, this is the first vector u, dot ev is going to be magnitude of this times magnitude of that times the cosine of the angle in between, so you get it going there. That's the magnitude of this thing in the direction of v. Or u parallel, another way to express this, is u dot v divided by v dot v. Now what is v dot v? Yeah, it's the magnitude of v squared. Okay? So that's the magnitude of v squared. So this, so you take v, divide it by its magnitude squared. This all does work out well. Those are all representations of the same thing. The scalar u dot v, this thing right here, is called the component of u along v, in the direction of v. In other words, how many multiples of that unit vector in the direction of v it is. Okay. This looks like, oh no, this is the proof. Now the only difference I see in my book and this one, this part down here in my book is green. The new edition, the old edition, I guess it was blue, or else the coloring people didn't get it colored right. Okay. If you think through what we were just saying, when this angle is obtuse, the first we showed was acute. When it's obtuse, then that dot product we were talking about before is a negative number. So that negative means it's in the opposite direction of the unit vector direction of v. Still collinear with it, but it's pointing in the opposite direction. Okay. When theta is obtuse, the u parallel, or projection of u, onto v and ev point in opposite directions. The same thing that we did before was true. Those hold up. It's just that term there is negative. Okay, this I think is then next page. I think this is example 6. Okay, find the projection of u, which is this vector right there, 5, 1, negative 3, along v, which is 4, 4, 2. And when I look at these two, I don't even see these are possibly the same vectors, and it's just not that they're not. But when I look at those two vectors, 5, 1, negative 3, that's going to have a magnitude of 25, 35, square root of 35.
A little under 6.
Second?
A little under 6.
Yeah. And V would have a magnitude of 32, exactly 6, right? Okay? And looking at that, they don't look like they're anywhere close. But remember, they're three-dimensional, so this one could be coming out of the board like this, so it's foreshortened, you know. So you can't trust the way things look. So find the projection of U, 5, 1, negative 3. Goodness gracious, can't write. Along V, 4, 4, 2, yeah. Okay. Now, find the projection of U. So what we're looking for is what they've been calling U parallel. They probably should be subscripted a little bit, but just wrote it poorly. How would you do this? We had a couple of different formulas you can use. Second? Okay. Times V. Okay? Yeah. The U dot V over V dot V times V. That would be the way I would go. Let's make sure that's the way. Yeah. They put a little V here. I just want to make sure I use the same nomenclature. Okay? Now, let's see what that turns out being. What's U dot V? 24 minus 6, yeah, 18 over second 36, okay, which is 1/2, right? Yeah, okay. So that's the same as 1/2 times angle V, which is 2, 2, 1. So there's U, the projection of U onto V, parallel to V. Okay? Yep, 2, 2, 1. That's what they got. All right. We now show that if V is not the zero vector, which we've been saying that repeatedly, then every vector U can be written as a sum of the projection of U onto V and the vector U perpendicular to V. In other words, U parallel to V and U perpendicular to V, that is orthogonal to V. Okay? So, yuck. So basically, and our book does, as soon as I go to write, it's going to shrink, and if it shrinks, I'm going to not really have room to write, but I'll try, okay? Sort of a catch-22 here. Probably didn't need this. No. Okay. Okay, those are V's in there. So Huh?
So small.
So, yeah, I know, but if I try to write them big, it reduces it. So our book, our new edition of the book puts these in the previous edition didn't. So just to make this consistent. The U is the component of U parallel to V plus the component of U perpendicular to V. That's always going to give you that U, the vector U. Okay. And this equation here is called the decomposition of U with respect to V. How do you decompose U parallel and perpendicular to V? Ask again, have all of you had physics or not? No, Matt hasn't. The rest of you have. What is this? This is it's work. It's, you know, everything that uses dot products, pretty much. Your inclined planes, you know, what you're doing is component of the force parallel to the plane, perpendicular to the plane. That would be the normal force. This is the applied force or the retarding force or something like this. So you are doing this kind of stuff big time. You know, you write down the gravity vector, weight vector in the component with the plane and perpendicular to the plane. You do it all over the place, okay? So it's not just a mathematical construct abstractly out there in space somewhere. It's things we really use. Okay, example 7. Find the decomposition of U, with U being the vector (5, 1, -3). Okay? With respect to V, WRT, with respect to V, and V is 4, 4, 2. They love that vector, don't they? We've had it now in about 3 different problems. Okay?
You said 2 but wrote 3.
Huh?
You said 2 but wrote 3.
All right, what's wrong with you, huh? Why would you do that? All right. 2. All right. Okay. All right. Find the decomposition of that vector with respect, U with respect to V. All right. Where you want to begin? We know how to do U parallel to V, right? How's that? U dot V over V dot V times V. Okay? And let's do that. U dot V is, Dewey does not have this. Oh, yeah, that's exactly the one we had before. Okay, we already got that. 2, 2, 1. Okay. Okay. No, that's the whole thing. I thought that was a part of it. No, that's it. Yuck. Keep doing this and it doesn't show up. There we go. 2, 2, 1. All right. Done. Okay. What we need to find is U perpendicular to V. How are we going to do that? What's that?
So the U minus U parallel to V equals U perpendicular to V?
Okay. Because we know this, we can find U perpendicular to V by starting with vector U and subtracting from it U parallel to V. Okay? So we know what U is, or what U are, okay? 5, 1, -3 minus MTH227, what would be that vector?
-1,
3, what do you say, -1?
-1, -4.
-4. Perfect. There is a vector perpendicular to V and its projection. And of course, then when you add those two together, you get that. Pretty straightforward. Okay. 3, -1, -4. Good. Let's see about example 8. This is an inclined plane problem, just like I was talking about before. What is the minimum force you must apply to pull a 20-kilogram wagon up a frictionless path ramp inclined at an angle 15 degrees? Okay. Sort of feels like a physics problem, doesn't it? I think what I'll do is erase all this from the slide. Can I do it? Y'all finished with this problem? Okay. All right. What's the minimum force you must apply to pull a 20-kilogram wagon up a frictionless ramp inclined at an angle of 15 degrees? All right. Let's see if I can get as much of that as I can drawn in there. Here it supposedly is your horizontal path. Here's your ramp. This way, we're assuming this is 15 degrees, okay, and here, the wagon, here you pulling it, you're a sort of pathetic looking stick man. Okay, you're pulling the wagon up the hill, up the plane, and this is a 20-kilogram wagon. What does that represent? Mass. The mass of the wagon is 20, goodness, I can't hardly write, kilogram. 20 kilograms. In addition, huh?
I was afraid you were about to go into another sneezing fit.
No, okay. I did Thursday, I guess it was. Oh man, no, it's not sneezing. My head's all clogged up, and there's 2 or 3 potential reasons for this. Number one, over the weekend I did a lot of yard work, spreading pine straw, which is really dirty pine straw, some of the worst I've gotten, at Home Depot. So it was dusty. I was spreading cypress mulch, which was not bad, but it was dry and ragweed, all that kind of stuff. And then I washed some exterior windows yesterday and stuff, so I was wet, so that could have clogged me up. But then, this has just been a really great day from the very beginning. At 3 o'clock this morning, I was pretty well asleep, and our alarm went off. Exactly at 3 o'clock. And when that happens, something like that, it's something to do with the system. Because I know they poll the system at some time, usually in the middle of the night. They dump data. They do something. And they did it exactly at 3 o'clock. And whatever they did made the alarm go off. There was nothing wrong, nothing wrong. It just went off. 3 o'clock. So I got up, and rather than mess with it, I found I knew where the battery was. I unhooked the battery, just so I could go back to sleep. About 30 to 40 minutes later, it went off again, mostly probably because since the battery was unhooked, I don't know, and it went off again. So that meant I had to go down and find the command to get it to shut down. We hardly ever use it, but we have it for insurance purposes. So I did that. So downstairs, dog upset and stuff. So I got it done and went back to bed. So it was probably 3:45. Sometime around 4:15, the dog starts barking. found out later it's because the police came through, because the company notified the police. Of course, I didn't hear them. I was enough asleep, but I could hear the dog barking, and I could not get her to shut up because she was scared. You know, she was worried with all the noise, and then with the people walking around outside, and she kept barking about every 5 to 15 minutes for the rest of the morning or night or whatever you want to call it. Till finally I got up at 5:15. So that probably also contributed to not being able to breathe well. I don't know. Okay, so here we have the picture. Okay, now what is the minimum force you must apply to pull this wagon up a frictionless ramp at an angle of 15 degrees? How would you proceed with this? This force is a vector, basically, and I have it done poorly. Let's have it horizontal here so we don't have anything to do with the angle there. Yeah, parallel to the plane. Okay. The mass times acceleration due to gravity gives you a weight this way. So the weight is 9.8 times 20, which is 19.6, right? Newtons. That's the force. Okay? Now what you're going to do is break that force into a component perpendicular to the plane and a component parallel to the plane. Okay? Now, where in that triangle I've just done is my 15-degree angle? Yeah, that's the one right up here. So that's 15 degrees also. Okay? This is 15 degrees, that's 15 degrees. So, what is the minimum force you would have to do to pull it up the plane? That's this parallel component of that weight. And what would that be? By the way, this is your 90 degrees. That's the perpendicular. So this is a hypotenuse. And that is this component here, which is the force we're looking for. That's the sine. The sine, 15 degrees, times that 19.6 newtons. Okay? Plug that into your old calculators, if you've got one. Now we're in degree mode. I said that, well, let's see, y'all put me in degree. No, they gave it to us in degree mode. Okay. So, anyone got an answer yet? Second. Times the sine of 15 degrees. 9.0. Huh? 5 point. That's what I was going to say. This seems too big. 5 point what? 0.07 newtons. Okay. How did they do in the book? They got 50. Oh, wait. Yeah, wait. Yeah. 20. Yeah, I'm sorry. I did 2 times. Yeah. Sorry, 20. 196. And that would be 51.7, which is about 50.7, which is about 51 newtons. And why 51? Because this is 9.8, 20. You don't have more than 2 digits anyway. 51 is good. 51 newtons approximately. Okay. Okay. And by the way, I drew mine kind of backwards. This component really should be going that way and this one that way. But I was already turning it around to what you would have to pull up the hill, up the ramp. Okay. Then the last thing here is a graphical insight between these two vectors. Oh, shoot, if I'd have known they had it drawn, I wouldn't have had to draw my own, but here they have it. And notice they do have the guy pulling parallel to the ramp pretty close. That way you don't get into all the other forces acting on it. Okay. Notice here, this is sort of a silly thing about the problem. If this is indeed a frictionless ramp, good luck with that, Jack. Why? He's not going to be able to walk up the ramp anyway if there's no friction there for him to pull it. Yes, right? He's going to be sliding down the ramp too. But, you know, we assume he's got enough friction somehow, or gravity shoes or something. Okay, never mind. We won't go there. Okay. This is our graphical insight. It seems we're using the term component in two ways. We say that the vector U has components A and B, okay? On the other hand, U dot E, that's a unit vector in the direction of E, is called the component vector of U along the vector E, okay? So basically what they're saying is, now let's just deal with the plane now, not free space. If we say this vector U going out in that direction has a component in the I direction and one in the J direction. So A, B, where A is a component in the positive X direction, B is a component in the positive J direction. However, that same vector U, if you're referring to not the XY coordinate, but some other vector B, and this is a unit vector along that vector B, then I can't recall seeing them use the unit vector E and then another unit vector F, but it's perfectly okay to do so. Then this is component in the direction of that new vector, and here's that one. Not the same as the components on X and Y here. In fact, they're not on X and Y. They're along the vector B and perpendicular to the vector B. So yes, they have two components. Components relative to the XY coordinates, that's your AB here. And this would be, this A still refers to XY. You know, that's the definition of A and B, components X and Y. But you also have components in the direction of the unit vector and perpendicular to the unit vector. Okay. So to me, that's not all that insightful, but they wanted to make a big point about it. Okay, and one other thing to remember, not just one, a major thing to remember is that the dot product of a vector with itself is the square of its magnitude. Okay, that's an easy way to, well, I mean, it's how you can compute magnitude anyway, but that's one way too. And following that, U dot or V dot W, this is one definition of a dot product. Is magnitude of V times magnitude of W times the cosine of the angle in between. As if you know the angle in between, that way you can calculate a dot product. If you know the components, you don't need that angle in between. All you have to do is multiply the corresponding components and sum those up. Okay? Oh boy, another one of these. Okay. All right. This is basically your definition for components of a vector in the direction of some other vectors, u in the direction of v perpendicular to v. Okay? And the one parallel to v is the unit vector along v times whatever that magnitude is. It's like it's about 2 there. Okay? And that's followed by, we've had all these before, but they're showing them again here in the summary. The component of a vector parallel to another vector is the dot product of the vector in question with the unit vector in the direction of the second vector multiplied by that second vector. This just gives you the magnitude of this vector in that direction, and then that is the direction. Okay? And then splitting this out a little bit, remembering that ED, if I can get this right, is another way of writing this component is dot product of u and v over the dot product of v with itself times v. That to me is the basic one to remember, and get this one off of that. And then u perpendicular is u minus u parallel. Easy to calculate u parallel, and then it makes it really easy to calculate u perpendicular. Now, this is component of u along v would be u dot v, u dot ev, and that's the same as magnitude of u times the cosine of theta. Okay. Okay, just making sure I've got them all. That is the end of the slideshow. I assume you probably want to do the exercises. Is that right? So let's do them here. I mean the preliminary questions. Is the dot product of two vectors a scalar or a vector? Say again? Scalar, absolutely. Okay, number 2. What can you say about the angle between A and B if A dot B is less than 0? Obtuse, very good. Number 3, which property of the dot products allows us to conclude that if V is orthogonal to both U and W, then V is orthogonal to U plus W? Which property of dot products? The what? It is one like a distributive property. Which property of the products, dot products, allow us to conclude? Yes. Okay. I also want to say the linearity property, but I'm not sure that we've gotten that far to talk about that. Let's see which one they refer to in the back. This is 12.3. Okay, scalar obtuse, yeah, you call it distributive law. That's exactly what they call it. It's also a form of linearity. That's more from linear algebra, though. Sorry. Okay. Number 4, which is the projection of V along V? Is it V or is it EV? What is the projection of V along V? Is it V or is it EV? Projection of V along V, these are both vectors. Is it V or is it the unit vector in the direction of V. Unit vectors, I usually put a caret over them to remind myself we're talking about a unit vector. Okay.
V?
I would say V too, but think this way. What is U? Projection of U along V. We had that before. What was it? U dot V over V dot V. That's a scalar, because both of those times V. Okay, so let's do the same thing. That would be V dot V over V dot V times V.
Not V dot U?
No. We're substitute. I'm sure. I should have put it up here.
Oh, V along V.
Yeah, so substitute V for U, and then that would be this, and this is exactly 1 times V, so that would be V, not EV. EV is a nice gal, but we're not going to deal with it. Okay. What are we? 12.4 or 12.3? No. 12.3. Oh, it gave a letter for it. Yeah, 8. Right. I just left off the other letter. Okay. Number 5. Let U parallel to V. Okay. Be the projection of U along V. Okay. Which of the following is the projection of U along the vector 2V? U projection okay. And which is projection of U of 2U along V? Okay. Now, A is 1/2.
That would be U along
2V. Agreed. V, U projected V.
That's just U along V.
That's the same thing. And C was 2U along V. Okay.
That's all that we're asking.
Right. This is A, that's C. Okay? I don't know how they answer this in the back. I think that's exactly what they do. Oops. Might help to get the right chapter. First, whoa. They said B and C. Oh, wait. It's not along 2V, it's along V. Okay, sorry about that. This is that one, not that. Okay? Because U along V, that's this thing. U along 2V is still that way. It's the same. And 2U along V would then be twice that because, So, First read, I'll stop that and then I misread and changed my mind. let's do 6. I'm going to erase all this. Do y'all need it any longer? Okay. 6. Which of the following is equal to cosine theta? Where theta is angle between u and v. However you put them. Okay. All right. Which of the following is equal to cosine theta? A, is it u dot v? B, is it u dot ev? Or is it C, eu dot ev? Okay. Which is cosine theta? By our definition, if you remember, cosine theta, remember, was u dot v over magnitude of u, magnitude of v, right? Say again? Yeah, okay. That's what cosine theta was. Yeah. You named it. It's probably listed on, yeah. U dot v, we did v dot w, but yeah. That's from dividing by that, yeah. So obviously not this one, okay, because you're off by a factor. Okay.
C.
Huh?
I said I want to say it's C.
B?
C.
C. Okay, C. I would say so because what isn't this? EU, and this is EV. Yeah. So it looks like it will be C. That means yes, in fact. Okay. And sure enough, it is C. Good deal. Homework exercises here. Do any of the odds 1 through 11, any of the odds 13 through 17. They go a lot faster than what we've done, I think. Either 19 or 21. Any of the odds 23 to 27. Do any of the odds 29 to 33. Do either 35 or 37. Either 39 or 41. And any of the odds 43 through 51. Any of the odds 53 to 59. Do 61. Do 63. And any of the odds 65 to 79. I mean 65 to 69. 71. Either 73 or 75. Wow, they got a lot of these. I'd say do 77. That's sort of a fun looking problem. 79 is supposed to be sort of a writing thing, but think through that. See if you get it right. And I'd say any of the odds 81 through 89. All right. There is also something in the further insights and challenges called a direction cosine that probably wouldn't be a bad idea to at least look at, think through, because you'll probably run into them again. But we'll pick them up if we need them. Okay, is there anything else left here? I don't think so.
We're doing 12.4.
Yeah, we're going to start 12.4. we go until 1:55, right?
Yeah, we got 12 minutes.
Yeah, okay. I've got 14 minutes. Okay. Okay. Yuck. I wasn't supposed to close all that out. Either I wasn't paying attention or it double clicked when I didn't mean for it to. So let's go back. Sorry about this. Open this up again. Four. I'll wake up in a minute, I think. It's gracious, my head hurts. Well, it hurts so much that my eyes are dry. Okay. It takes forever for this thing to do something. There we go. Now I got to get off of here. All right. Don't know if any of you have actually seen one of these before. Maybe you've seen pictures of them. This is called the bubble chamber. Okay, and this is a pretty lousy rendition. Your book probably is a little bit clearer than this. What's that? Yeah, and what you have is charged particles, which means you have electric fields going on here, but you also have a presence of a magnetic field, and when you have those together, you have basically cross products, and that's what makes the spiraling and the other, and the bending of the curves going on, because cross products, several differences between dot products and cross products. Can you give me one? A dot product, the result is a scalar. Cross product is a vector. Okay. Dot products depend on the cosine of the angle in between. Cross products depends on the sine of the angle in between. You should not necessarily know that yet, but we will be doing it. And here's another example of some pretty incredible things. And by the way, since they're mentioning them here, these would be potential paper topics as well. Who in the world was Van Allen that described these things? What are the Van Allen radiation belts? They're thousands of miles above the Earth's surface, made up of streams of protons and electrons that oscillate back and forth in helical paths between the two magnetic mirrors set up by the Earth's magnetic field. This helical motion is explained by the cross-product nature of magnetic forces. So again, you've got protons, electrons, which are charged particles moving, so that implies electric fields and magnetic fields. You get cross-product activities here. Now,
I want to say radiation belts and moves and stuff.
What's that?
And I said I want to say those move and stuff depending on what the sun is doing. Like they compress.
right.
That sort of thing.
Yeah, according to what you said, the sun was doing, yeah, sunspots and things like this really change these pretty dramatically.
So it'll like make the side really big and kind of compress the atmosphere on the side the sun is on.
There actually was some thought at some time that we could never do interplanetary exploration because we'd have to pass through the Van Allen belt, and that we wouldn't be able to. We as humans wouldn't be able to because it would kill us.
Of course, they thought similar things about trains and going so fast.
Yeah, so it probably would have thought the same thing about breaking the sound barrier and things like that. So man has not crossed, I don't think, the Van Allen belt yet. Spacecraft have, but I don't think a manned spacecraft has yet, because these are thousands of miles out there, you know. They're not near Earth orbit, you know. So it is pretty interesting. Now, don't confuse this with the ionosphere, which is a sphere around the Earth, and we have been through that several times, but I wouldn't be surprised if they thought that would kill us too, but who knows. So far they haven't. Yeah. Everything will kill you, it sounds like. Okay. Now.
I've been wanting to throw one of these vectors in a matrix for quite a while.
Yeah. We're going to get a little bit into a determinant here, and I'm really tempted not to go so awfully far into this. I want to basically just give you the definition of the cross product. We really don't have time for all this. You may have run into it before, but let's just go down to what the definition of a cross product is. Oh man, they give it in terms of that. So let's go back. Sorry. Yeah. Trying to skip something. Okay, I'm not sure if you recall this, and maybe you've never had it before. A determinant of a 2x2 matrix, really easy thing to do. You do the main diagonal, the product of the main diagonal times the product of the other diagonal. Okay, so the determinant of this 2x2 matrix is AD minus BC. Anything you're going upper left to lower right are positive products, and going in the opposite direction would be negative products. So AD minus BC. Okay. Now, I would have rather done this otherwise. Let's now do a 3x3 matrix. Okay? And you might say, what does this have to do with cross products? We'll get there. Okay? In a 3x3 matrix, this is one way to do it. Okay? The determinant is pick any element in any row, any column. Okay? One of them has to be row 1 or column 1. So they chose A1. Then do the determinant of this one. That number times the determinant of this 2x2. B2 C3 minus C2 B3. However you want to say that. All right. Then go to the next one. Now you could have gone here or here. It doesn't matter. But just pick a row, pick a column, and carry it forward. So here's a hint. Any size matrix you have, start upper left and do this. Plus, minus, plus, minus, plus, minus, plus, minus, plus, or plus, minus, plus, minus, plus, minus, plus, minus, plus. As long as you go either right or left, up or down, just change the sign as you go. Don't do any diagonals, okay? But those, and that determines the sign. So since you're going to B1 here, that's going to be a negative, because that's in a negative position. Then take the determinant that's left. When you wipe out that row and that column, that's what we did with here. You know, we did that determinant. This would be A2C2, A3C3, and do its determinant. Okay. Then this is a plus position, plus C1 times wipe out that row and column. The determinant is left. So that's one way to do it. There's an easier way, and I wish they hadn't done this, but it's absolutely correct. Perfectly fine. Okay. Now, with that in mind, then here's the definition of a cross product. Cross product of vectors A1, B1, C1, that's vector V, with vector W, which is A2, B2, C2 is set up your determinant, except the first row do I, J, and K. They're not components, they're just I, J, and K. And then do the coordinate or components of the two vectors you're going to cross. Okay? A1, B1, C1, A2, C2, B2. Order matters here. It matters big time. So be sure you get them in that order. First row is I, J, K. Second row are the components of V. And third row is the components of W. And then they're just going to cross things around a little bit. This determinant times I minus this determinant times J plus this determinant times K. Okay? Now, that's one way to do it. Let me show you what I feel like is the easier way. Okay? It gives you the same results. Okay? And of course, when I go to write, it's going to shrink this. I probably should have done it on the last slide, but I think it's better here. Let me just do it here. Oh, I probably already got it. Nope. 1 minute left. Okay, this shouldn't take long. All right. I'm going to do this one here. Determinant of I, J, K, A1, A2, no, B1, C1, A2, B2, C2. Okay, here's what you do. Repeat the first two columns. I, J, A1, B1, A2, B2. Okay. Now, here's what you do. Do upper left to downward right. Okay. That would be, yeah, I times B1, C2, okay, and then do from I again, do minus C1, B2, okay. J, go this way, and then minus this way. K, everything that's upper left to lower right is positive, in the opposite direction is negative. So that way you don't have to remember where my minus is, what you do. That says it all for you. What's that? Yeah, I was going to say I thought Dr. Bryant did it that way too. Okay, so we'll end there at cross product. We'll pick up next time. We may do example 2. Why not? Since we got it, we'll do it. And we'll do just a little bit more of this. We may not do the whole section, though a lot of it is pretty fun. But we need to move on. Good deal. We'll see you on Wednesday. Wasn't it good news to hear I wasn't going to cancel class today?
Oh, yeah.
Oh, yeah. All right. That's a good answer.
Wasn't
All right.
sticky enough.
Huh? Yeah. Right. His wife's in my first class, and she understood it to be that I would be canceling class after that one. I said, no. After my last class, I might just go home early today and change clothes. But it's not sticky anymore, so I'm going to hang with it.